Imagine a Windows endpoint that is already compromised. The attacker needs a reliable command channel, but a conventional malware beacon could expose both the implant and its server. Instead, the malware starts a separate copy of Chrome or Microsoft Edge with no visible window. It controls that browser through a local debugging interface and makes the browser create an encrypted WebRTC connection through legitimate cloud and communication services. The malware talks only to the loopback address. The trusted browser makes the external connections, and the attacker's real server stays out of the victim's packet capture. That is the central technique in msaRAT, a Rust-based remote access Trojan documented by Cisco Talos and attributed to the Chaos ransomware group. This is not a Chrome or Edge vulnerability, and ordinary browsing does not install the malware. The attacker already has access to the Windows machine. The browser is being abused after compromise as an execution and communications layer. We will follow the attack from a fake Windows update to a hidden command shell, explain why familiar defenses may miss it, and finish with a practical response checklist. The analysis is based primarily on Cisco Talos research published on July 23, 2026. Details may evolve as the campaign develops. Chaos is a ransomware as a service operation that uses double extortion. msaRAT appears after initial access and before the encryptor, so discovering it should be treated as a pre-ransomware emergency. In the observed chain, the attacker used the Windows curl utility to download a file named update_ms.msi into program data. The installer pretended to be a Windows update. One detail is especially valuable for detection: the destination used port 443, but the application protocol was plain HTTP, not HTTPS. A port number is not proof of encryption. Security controls should identify the actual protocol and flag plain HTTP on a port normally associated with TLS. When the installer reached its finalization stage, a custom action loaded an embedded lib.dll directly from the MSI binary table into memory. That DLL was msaRAT, and an exported function named run started the implant. The sequence is difficult to dismiss. A command line utility retrieves an MSI, writes it into program data, seksec runs it, an unusual custom action loads a DLL, and a headless browser appears with remote debugging enabled. Defenders should preserve the process tree, download origin, installer signer, loaded modules, and browser activity. Application control should restrict MSI execution from writable directories and require managed updates. After initialization, msaRAT searches for Chrome or Microsoft Edge. Once it finds a supported browser, it starts a new headless process through the Windows process creation interface. This is not the employee's normal browser window. It is a separate instance with a malware-controlled user data directory and a remote debugging port. Those options are strong detection opportunities. Remote debugging can be legitimate on test systems, but approved automation should have predictable parents, accounts, hosts, and schedules. On an employee endpoint, a browser launched by an installer-related process with no visible user session is highly suspicious. msaRAT connects to the browser's debugging service on 127.0.0.1. It requests the available browser targets, obtains a WebSocket debugging address, creates a new tab, and enables the page and runtime functions of Chrome DevTools Protocol. The RAT registers callbacks and injects JavaScript into the controlled tab. That script creates the external channel and reports events to the implant over the local debugging connection. Chrome and Edge are legitimate applications. The suspicious behavior is an unexpected process launching the browser invisibly, controlling it over loopback, and causing it to contact cloud signaling and relay services. Detection improves when endpoint teams join the local controller and the browser's external traffic into one causal sequence. The injected JavaScript creates a WebRTC data channel. WebRTC is a normal browser capability used for real-time audio, video, and data. It includes the networking features needed to cross common firewalls and network address translation. First, the browser contacts a Cloudflare Workers endpoint for signaling, which exchanges the descriptions needed to establish the session. Client-controlled headers made to resemble Microsoft-related traffic do not prove Microsoft-generated or approve the request. Next, Google Stun discovers the infected host's external network mapping, while Twilio TURN relays traffic when a direct peer-to-peer path cannot be formed. Here, the attacker deliberately forces the relay. Talos reports that the server's session description omits the candidates normally needed for a direct path and uses 0.0.0.0 as the connection address. The victim therefore connects to legitimate relay infrastructure while the operator's real address stays hidden. After the data channel opens, the signaling endpoint drops out of the main command path. Commands and results move through the TURN-relayed WebRTC channel. Blocking every Workers, Stun, or TURN service would disrupt legitimate applications. The stronger signal is their appearance immediately after an unusual headless browser launch and a local DevTools connection, without normal user activity. WebRTC data channels already use DTLS transport encryption. msaRAT adds another encryption layer using a ChaCha Poly 1305-based scheme. When the channel opens, the implant and server perform an elliptic curve Diffie-Hellman key exchange and derive shared key material for the command frames. The result is double encryption. The browser protects the WebRTC transport, and the RAT protects the application payload before handing it to the browser. Even if a security tool recognizes WebRTC, it cannot simply raid the attacker's commands. That changes which evidence is useful. Defenders can still ask which process launched the browser, which flags were present, which local process connected to the debugging port, and whether signaling, stun, and turn followed immediately. Command frames ultimately pass strings to the Windows command shell, and output returns through the same channel. A command prompt tied to an installer-loaded DLL or headless browser chain deserves immediate investigation. This is the weakness of reputation-only security. A trusted process does not guarantee trusted behavior. A trusted cloud platform does not guarantee a trusted tenant. Encrypted traffic is not automatically approved, and a local host connection is not automatically harmless. The best detection model is causal: what happened first, what enabled the next action, and whether the sequence matches an approved workflow. The highest value detection begins with the browser launch. Alert on Chrome or Edge started with headless operation, a remote debugging port, and an unusual user data directory. Add parent process and host context so approved development automation does not generate noise. Next, find a non-browser process connecting to the browser's local debugging port, followed by signaling, stun, and turn traffic without visible user interaction. Hunt for command line clients writing MSI files into program data, plain HTTP on port 443, and seek sec activity with unexpected custom actions. Monitor command shell ancestry and capture process trees, command lines, accounts, child processes, and file writes. The attacker still needs operating system actions to move laterally, stage data, and prepare ransomware. Use current Talos indicators as investigation pivots, not as the sole detection method. Behavioral detections will outlive a static block list. For hardening, require managed and signed software updates, restrict arbitrary MSI execution, monitor browser debugging features, limit WebRTC and turn where there is no business need, protect remote management tools with phishing-resistant authentication, and isolate backup and privileged management infrastructure from ordinary endpoints. Validate that your tooling records browser command lines, process ancestry, loopback sockets, DLL loads, seek sec behavior, and command shell execution. If msaRAT is suspected, isolate the endpoint while preserving volatile evidence. Capture the process tree, browser command line, debugging port owner, active loopback sockets, browser profile directory, loaded modules, current connections, and memory associated with the installer and RAT. Preserve the MSI, DLL material, persistence, endpoint records, proxy logs, DNS data, and remote management sessions. Revoke credentials and active tokens used on the host. Hunt for the same delivery source, signaling domain, installer metadata, browser options, debugging behavior, and process sequence, including variants with different names or destinations. Investigate the original access path, including phishing, help desk activity, remote support, exposed services, and anomalous sign-ins. Then look for credential access, lateral movement, data staging, backup discovery, and ransomware preparation. Do not stop after blocking one address. Remove the attacker's access and rebuild from a trusted source when integrity cannot be established. The strategic lesson is simple. msaRAT combines legitimate browser debugging, real-time communications, cloud services, and encryption into an unauthorized control system. Viewed separately, the parts may look normal. Viewed as a sequence, they reveal a pre-ransomware intrusion. This video is general education and news commentary, not legal, compliance, or incident response advice. Never access or test systems without explicit written authorization. CipherVibe is a cybersecurity market intelligence publication operated by CloudSecTech LLC. Read the full sourced analysis at CipherVibe.com.